After extensive upgrades and maintenance, the renowned Large Hadron Collider, or the LHC at CERN, roared back to life in April 2022, kicking off an extraordinary scientific endeavor known as Run 3 that promises a series of mind-boggling experiments scheduled to hold the world's attention until 2024. On the other hand, CERN has made some other frightening news lately regarding activating the iconic Large Hadron Collider. Join us as we investigate the astounding possible risks revealed by scientist Michio Kaku. The European Organization for Nuclear Research, also known as CERN, which operates the Large Hadron Collider, or the LHC, reported that its scientists discovered the first evidence of an unusual mechanism by which the Higgs boson decays into a Z boson and a photon. The discovery of the Higgs boson, also known as the God particle in 2012, was a watershed moment in particle physics research. Since then, scientists working with the ATLAS and CMS experiments at the LHC have been studying the particle's properties, attempting to understand how it's generated and decays into other particles. ATLAS and CMS researchers presented evidence of the Higgs boson decaying into a Z boson and a photon at last month's Large Hadron Collider Physics Conference. The Z boson is the weak forces electrically neutral carrier, while the photon is the electromagnetic forces carrier. According to CERN, this disintegration could give indirect evidence for the existence of particles other than those anticipated by the standard model of particle physics. The standard model best explains all phenomena connected with elementary particles or the universe's building blocks. CERN, known as one of the world's largest and most prestigious scientific research facilities, employs scientists, physicists, and engineers in their quest to answer science's most vexing issues. Their investigations span from diving into dubious notions to investigating other realms of dark matter. Intricate and advanced scientific tools beyond comprehension aid these endeavors. CERN has made groundbreaking discoveries such as neutral currents and the Higgs boson, dubbed the God particle by the scientific community. Let's explain the Higgs boson first. The Higgs boson is the primary force-carrying particle of the Higgs field, responsible for the mass of other particles. This area was first postulated in the mid-1960s by Peter Higgs, the particle's namesake, and his colleagues. The LHC verified the presence of the Higgs field and the mechanism that produces mass, completing the standard model of particle physics, the most incredible description of our subatomic universe. According to CERN, the Higgs boson has a 125 billion electron volts mass, making it 130 times more massive than a proton. It is also chargeless and has no spin, which is the quantum mechanical counterpart of angular momentum. The Higgs boson is the only elementary particle with no spin. A boson is a force carrier particle that enters the picture when particles interact, exchanging a boson throughout the contact. When two electrons interact, they exchange a photon, the force-carrying particle in electromagnetic fields. Because quantum field theory uses wave mechanics to describe the microscopic world and the quantum fields that fill the cosmos, a boson can also be represented as a wave in a field. A photon is a particle and a wave that emerges from an excited electromagnetic field. In contrast, when excited, the Higgs boson is the particle or quantized manifestation that appears from the Higgs field. That field generates mass through its interactions with other particles and the Brout-Englert-Higgs process carried by the Higgs boson. One of CERN's continuing pursuits is the search for magnetic monopoles, which satisfies the thirst for scientific knowledge. Magnetic monopoles are particles that have only one of the poles, as opposed to conventional magnetic particles that have both poles. Magnetic monopoles have escaped scientists for a century, despite their theoretical existence. This pursuit led to the invention of colliders. Colliders are designed to create particle collisions, allowing scientists to investigate the aftermath and gain significant insights. But researchers predicted that colliders would give birth to monopoles. So yet, none have been discovered, due to the search for new particles, including monopoles. CERN built the Large Hadron Collider. Let's look at what the LHC is. The Large Hadron Collider, or LHC, is the world's largest and most powerful particle accelerator. It became operational on September 10, 2008, and is still the most recent addition to CERN's accelerator complex. It's a 27-kilometer ring of superconducting magnets with several accelerating components to raise particle energy. Two high-energy particle beams move near the speed of light inside the accelerator before colliding. The beams flow in opposite directions in separate beam pipes, two ultra-high vacuum tubes. A strong magnetic field, maintained by superconducting electromagnets, guides them around the accelerator ring. Electromagnets are constructed from coils of special electric cable that work in a superconducting condition, efficiently transmitting electricity without resistance or energy loss. This necessitates cooling the magnets to -271.3 degrees Celsius, colder than outer space. As a result, much of the accelerator is linked to a liquid helium distribution system, which cools the magnets and other supply services. Thousands of magnets of various types and sizes are used to steer the beams around the accelerator. There are 1,232 dipole magnets, 15 meters long, that bend the beams, and 392 quadrupole magnets, 5 to 7 meters long, that focus the beams. Another magnet is employed just before the collision to squeeze the particles closer together, increasing the likelihood of collisions. Because the particles are so small, causing them to collide is analogous to firing two needles 10 kilometers apart with such precision that they meet halfway. The CERN Control Center houses all of the accelerator's controls, surfaces, and technical equipment under one roof. The beams inside the LHC are then made to collide at 4 points around the accelerator ring, corresponding to the positions of the 4 particle detectors: Atlas, Alice, CMS, and LHC-B. The scientific community cheered after 3 years of waiting when the LHC eventually became operational, completing the European Union's aim to enhance our understanding of the universe, which had been methodically developed over several years. From its inception, the LHC proved to be an important instrument for scientific investigation. It was a daunting endeavor to build such a complicated machine. Still, through high-intensity collisions within the LHC, scientists got significant insights into the intricate structure of the subatomic realm. While collisions occur naturally in our atmosphere daily, the resulting product of smaller particles decays quickly, making them difficult to examine in their natural context. The huge tunnel of the particle collider is the only way to explore them adequately. This magnificent building was built between 1983 and 1988 at around 7.5 billion euros or $9 billion, making it one of the most expensive scientific instruments ever created. With around 600 million particle collisions per second, the LHC and its simulations generate an estimated 15 petabytes of data each year, and 1 petabyte being comparable to 1,000 terabytes. CERN scientists face a huge barrier in reviewing such a massive amount of data, which is why the LHC is a joint endeavor, including scientists from several countries, including Michio Kaku. While the LHC began operations on September 10, 2008, a magnet quench problem prompted a year-long delay. The incident damaged over 50 superconducting magnets and associated components during the initial testing period. Finally, in 2010, the LHC had its moment of glory when protons and lead nuclei collided head-on at incredible energy, revealing unparalleled scientific phenomena from 2010 to 2013. However, the journey continued. The CERN team recognized the need for additional upgrades to this super collider. As a result, the LHC was temporarily shut down in 2013, rebuilt, and restarted in 2015, following a 2-year refurbishment known as the Long Shutdown 1, or LS1. During this time, CERN improved the LHC's accelerators and detectors and replaced critical magnetic components, allowing the device to operate at full power. As a result, the LHC reawakened in 2015 with enhanced powers, pushing scientific research boundaries and unlocking new knowledge channels for humanity. However, the Large Hadron Collider LHC shut down again in 2018 to make more improvements targeted at increasing its luminosity. The rate of collisions in a collider is referred to as luminosity, and it is an important aspect in obtaining relevant data for scientists. The LHC's operating organization, CERN, intended to explore deeper into the mysteries of monopoles and dark matter. Science fiction fans will recognize these concepts. Dark matter is a material that exists in space and has qualities like the inability to absorb, reflect, or emit light, making it undetected by normal means. Dark matter, according to scientists, appeared immediately after the Big Bang. One of the key goals of the improved LHC was to discover the secrets of dark matter. However, the LHC produced unanticipated results, resulting in a disaster rather than a breakthrough. Scientists at CERN revealed a stunning discovery after the LHC was restarted in April 2022 with the new maximum beam energy, conserving Earth's magnetic field upon activation. The LHC identified an abnormal fracture in the Earth's magnetic field, a previously unknown event. The Earth's magnetic field has polarity opposition between its north and south magnetic fields, resulting in a partial cancellation and the formation of a tiny gap at the equinoxes. On the other hand, this specific fissure remained open for an astonishing 14 hours. It's crucial to note that this crack did not allow beings from other dimensions or worlds to enter, because the Earth's magnetic field does not act as a protective barrier against such occurrences. Rather, its primary job is to shield the Earth from the tremendous solar winds. The Earth's magnetic field and the ozone layer play an important role in moderating the negative impacts of solar activity. If allowed unchecked, the solar winds could have disastrous implications, such as the disintegration of the ozone layer. These winds are also responsible for the breathtaking auroras that may be seen in the sky. Although these natural occurrences appear enchanting from Earth's perspective, they pose substantial dangers to satellites and electrical networks, potentially causing massive blackouts. As a result, NASA actively monitors and records the Earth's magnetic field, and recent investigations have revealed a considerable loss of its intensity. Of particular worry is the South Atlantic anomaly, which spans South America and Southwest Africa. The Earth's magnetic field is key to preserving our planet's stability. It allows compasses to point north reliably and aids animal navigation during long-distance migrations. Furthermore, it protects our atmosphere from the destructive impacts of solar winds, emphasizing its critical role in protecting the well-being of life on Earth. The activation of the Superbeam Collider may have resulted in weakened regions, but this is unknown. On the other hand, the incident with a broken magnetic field line suggests a link. These weaker areas pose a huge hazard, particularly to satellites and vehicles in orbit. Critical communication services in our contemporary society, like telephones, radios, television, and the internet, rely significantly on satellite technology. As solar flares become more common, these craft will be more vulnerable to their impacts than humans. Solar flares not only produce heat, light, and radiation, but they also cause coronal mass ejections. CMEs are huge explosions on the sun's surface caused by instabilities in the magnetic field. CMEs can create nationwide blackouts and damage communication infrastructure, as Elon Musk's loss of 40 SpaceX satellites revealed. These storms carry electrical charges and heat when approaching Earth in early 2022 during a solar storm. While producing spectacular displays such as the Northern Lights, they can also cause chaos and pose hazards. NASA stated that two enormous flare outbursts travel approximately 2 million miles per hour toward Earth. If a storm occurs, we could see disturbances in radio navigation frequencies, satellite malfunctions, and even global internet outages, potentially costing trillions of dollars. Historical events such as the 1989 Quebec incident and the 1859 Carrington event highlight the catastrophic power of solar storms. Nonetheless, they provide breathtaking sky decorations. The recent turn of events shows that such a storm could occur again. Scientists are still figuring out how the Sun and Earth's magnetic fields work. Utilizing the Large Hadron Collider may have contributed to faults in the magnetic field system that allowed solar winds to enter. There has been speculation, such as CERN opening a portal to another dimension. While these theories have yet to be validated, there have been concerns regarding the LHC's impact since its inception in 2008. To avoid a dark day for humanity, scientific societies, including CERN and other research organizations, must work together to mitigate the risks of approaching solar storms. The days are getting longer, the trees are getting greener, and it's also time for the CERN Accelerator Complex to come back to life. Following the year-end technical halt, or YETS, a 17-week period during which the accelerators are maintained and minor upgrades are performed, each accelerator in the chain has restarted for the 2023 data-taking season. Each restart is a critical stage in transporting protons from their origin to their eventual destination in the Large Hadron Collider. While most substantial machine modifications were completed during the protracted outage preceding the commencement of LHC experiment number 3, accelerator upgrades completed during the YETS will boost physics data taking for the second year of the experiment. Thanks for watching. Share your thoughts in the comments section and subscribe to our channel for more quality content.